Okay, so we're in section 9.3 today, and 9.3 and 9.4 are concerned with a number of different identities that can all, in a certain sense, be traced back to our sum and difference formulas that we talked about in 9.2. So 9.2 really set the stage for the following two sections. So let's go ahead and just get into it. Like the name suggests, there's three categories of identities we're looking at: double angle, half angle, and reduction formulas. And we're going to start by looking at these double angle formulas. So the first question is, what is a double angle formula? When we say double angle formula, we're talking about an identity in particular that deals with expressions of these types: sine of 2x, cosine of 2x, tangent of 2x. You have an angle x, you double it, and then take sine, cosine, or tangent of those. We're not going to derive any of these types of identities for secant, cosecant, and cotangent. And the reason for that is because it's kind of unnecessary. If we can develop identities that give us sort of formulas to work with, given any one of these three expressions here, then the other three trigonometric functions are just going to look like reciprocals of the things we get for these. So let's go ahead and find a double angle formula for sine. Starting with this, sine of 2x. Remember, I could put parentheses around that 2x, saying that the very first thing I'd be doing is doubling the x and then taking the sine. So if I did put parentheses around that, 2x could be alternatively written as x plus x. And the reason I would do that is because this puts my expression in a form that allows me to use my sum identity for the sine function. This is like sine of alpha plus beta, but alpha and beta are both equal to the same thing in this case, x. So remember, the sum formula for sine looks like sine of the first angle times cosine of the second angle. That would be sine of x, cosine of x, plus cosine of the first angle times sine of the second angle, cosine of x, sine of x. But by the commutative property for multiplication, sine times cosine is the same thing as cosine times sine. So these are really the same term. And by adding something to itself, we get 2 times that, 2 sine of x, cosine of x. And so that's our double angle formula for the sine function. Sine of 2x is equal to 2 times sine of x, cosine of x, for any angle or any value of x that I could plug in to that. Okay, that one was fairly straightforward. Again, just using our sum identity. We want to follow the same pattern to develop an identity, a double angle identity for the cosine function. And in fact, we're going to not just stick with one double angle formula for cosine. Once we get the one we're going to derive here, we can actually derive 2 more, giving us a total of 3 different double angle formulas for the cosine function, each of which can be useful in different cases. So same pattern, cosine of 2x can be written as cosine of x plus x. And then if we use our sum formula for the cosine function, that's cosine of the first angle times cosine of the second angle, minus, remember this plus becomes a minus here, sine of the first angle times sine of the second angle. But again, that's the first and second angle are the same. So this is really the same thing as cosine squared. And this is the same thing as sine squared. And here we have our first double angle formula for the cosine function. Cosine of 2x equals cosine squared of x minus sine squared of x. Now, where we get the other 2 identities that I alluded to before is by taking either the cosine squared here or the sine squared here and changing the way that looks using our Pythagorean identity. So here's what I mean by that. Let's take the cosine squared. According to the Pythagorean identity, cosine squared is the same thing as 1 minus sine squared. We found that to be a really useful identity in 9.1. So making a substitution here, cosine of 2x, according to what we did up here, is equal to cosine squared minus sine squared. But if I were to take this cosine squared and replace it with 1 minus sine squared, that's where I'm using my Pythagorean identity. I still have another minus sine squared here. So combining like terms, this is the same thing as 1 minus 2 sine squared of x, since there are 2 of these. Okay, so that gives us our second double angle formula for the cosine function. If I do essentially the same thing, but replace sine squared of x with 1 minus cosine squared of x, then you can follow the same kind of simplification process, and in this case we end up with 2 cosine squared of x minus 1. So 3 different double angle formulas for cosine. It's the only one that we develop more than one double angle formula for, and that's because that ends up being really useful when we're developing the half angle and reduction formulas that come later. Okay, now how do we do tangent of 2x? Same idea. We have an angle sum formula that we developed in the previous section for tangent, so I would rewrite 2x as x plus x. And using that angle sum identity, tangent of x plus x would equal tangent of x plus tangent of x, first and second angle there, over 1 minus tangent of x times tangent of x, first and second angle there. Simplifying, I have 2 of the same term up here that becomes 2 tangent of x, and then tangent times tangent can be written as tangent squared, and this is what we end up with. So to summarize all of that here, we have a table giving us all 3 of those functions and their double angle identities. And notice the double angle identities for cosine, we have 3 of them that we want to have in our toolkit. Okay, so let's try using some examples, or looking at some examples where we want to use these. Here it says given sine of theta equals negative 2/3, where theta is in the 3rd quadrant. We want to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. How do we go about this? Well, first of all, notice that all 3 of those, sine of 2 theta, cosine of 2 theta, tangent of 2 theta, can be written in terms of sines and cosines where the angle is just theta instead of 2 theta. In particular, we need sine of theta, cosine of theta, and tangent of theta in order to get all of this stuff. And one of those 3 things we are given already. So sine of theta equals negative 2/3. If I can find cosine of theta from this and tangent of theta from this, then I have enough information to do what it's asking me to do. So can we come up with that? Of course. What I'm going to do is use the information I'm given to sort of sketch this angle, or create a reference angle for it in the 3rd quadrant. So here's my reference angle, and then remember, sine of theta, if this is my angle here, would be opposite over hypotenuse, negative 2/3. Remember, the reason we want this to be a negative 2 is because, again, it goes below the x-axis where all of my y-coordinates are negative, so I interpret that as a negative number. Then I could use the Pythagorean theorem with these values to determine the length of this side of my right triangle. So that would be root 5. And again, I'm leaving off the work that shows that, but we've done this so many times that hopefully you can kind of fill in the blanks there. Okay. Let's call that theta. So now, having all 3 sides of this right triangle, I can easily find cosine of theta and tangent of theta. What is cosine of theta? Cosine of theta is adjacent over hypotenuse, which would be, I almost forgot to do that. I want to make that a negative root 5 because, again, this is on the negative x-axis here. And remember, we interpret cosine as the x-coordinate of a point on the unit circle. We could also alternatively just remember that because theta is in the 3rd quadrant, where cosine is always supposed to be negative, that this needs to come out to a negative value, negative root 5/3. Tangent of theta, what is tangent of theta? Opposite over adjacent, which would be 2/5. Okay? So now, let's do what they're asking us to do, sine of 2 theta. According to our double angle formula, sine of 2 theta is equal to 2 sine of theta cosine of theta. But we have sine of theta and we have cosine of theta. This is the same thing as 2 times negative 2/3. Cosine of theta, again, that's negative 5/3. This simplifies to 4 root 5/9. Okay, so there we have it. Next step, I'll circle that. We want cosine of 2 theta. And remember, cosine, you have 3 different double angle formulas to choose from. And it doesn't matter which one you choose, in this case at least. because I have enough information to use any of those. So let's use the first one that we came up with. Cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. And remember, I have cosine and I have sine. Cosine is negative root 5 over 3. We're squaring that. Minus sine squared, negative 2/3 squared. This would equal 5/9 minus 4/9, or 1/9. Okay? Finally, we want tangent of 2 theta. We only have one double angle formula that we can use. It's equal to 2 tangent of theta over 1 minus tangent squared of theta. And remember, we know tangent, it's 2/5. So this would equal 2 times 2/5 over 1 minus 2/5 squared. Okay, what would that equal? 2 times 2/5 is 4/5. 2/5 squared is 4/25. 1 is the same thing as 25/25, so that gives me a common denominator. 25 minus 4 would be 21/25. Okay, how does this simplify? I know I normally don't do the fraction arithmetic, but this might help some people who still are kind of struggling a little bit. You could take the reciprocal of the denominator and then multiply. I get a 1 there and a 5 there. 20 over 21 is my answer. All right, so there we have it. There's all three things that they asked us for. Let's take a look at a different example. This one is saying, let's write cosine of 12x in terms of cosine of 6x. What does that mean? Well, first of all, we should expect that we want to use a double angle formula here, because that's all we've talked about yet in this section. And 12 is twice as big as 6. So that means cosine of 12x can be written as cosine of 2 times 6x. Okay, so that came out a little bit sloppy. So 2 times an angle, which is 6x. That 6x is now playing the role of the theta in this double angle formula, or any one of these double angle formulas. The next thing I want to look at is the fact that it's asking me to write cosine of 12x in terms of cosine of 6x. It doesn't say cosine of 6x and sine of 6x. It just says cosine. So this is where I have to be careful to select the correct double angle formula. Only one of these three double angle formulas is written entirely in terms of cosine, and it's the third one. Notice the other two have a sine in there. So I want to specifically use my third double angle formula down here, 2 cosine squared of theta minus 1. The only difference is that instead of theta, we have 6x. So that means this should look like 2 cosine squared of 6x minus 1. And that's doing what it's asking me to do. The cosine of 6x is the only trig function that's showing up in this expression, but I managed to reduce the size of that coefficient by using this double angle formula. So that one was pretty quick once you know what you're looking at. Let's try one more. In this case, we're proving an identity. So the identity that we're looking at is cosine to the 4th power of x minus sine to the 4th power of x equals cosine of 2x. Now in this case, I'm actually going to start on the left-hand side, and if I use some of my algebra knowledge, this ends up being not too difficult to do. So cosine of 4x minus sine, of 4x, sine to the 4th of x, cosine to the 4th of x there. If you've been working at factoring polynomials a lot, you may recognize the form of this thing. It's kind of like a to the 4th minus b to the 4th. That's technically a difference of squares. This thing is going to factor to cosine squared of x plus sine squared of x times cosine squared of x minus sine squared of x. Okay, now looking at each one of these expressions, this should look really familiar. Cosine squared plus sine squared by the Pythagorean identity we know is equal to 1. But now we also should be recognizing this, cosine squared of x minus sine squared of x. That was the first of our double angle formulas for cosine. So that thing is equal to cosine of 2x. And of course, 1 times anything is itself. So cosine of 2x is what comes out of that. That's what we were being asked to prove. Not too bad, not too bad. And again, remembering how to factor polynomials is very, very useful in this entire chapter. So hopefully that made sense. Okay, so that was a little bit on double angle formulas. Next up, we're going to talk about reduction formulas. Reduction formulas are really useful in calculus, mostly calculus 2, when you're doing integration. And the idea here is that we are given some trigonometric function that's raised to a power, like sine squared, for example. And the idea is to put this thing into a form where the exponent, that power, that 2 here, is decreased. That's why we call it a reduction formula. And the reason for that, again, is not something I can motivate in its entirety right now because it's a Calculus 2 topic. But in Calculus 2, you spend a lot of time talking about integrals and integration. And what you're integrating is functions. So you might ask somebody to integrate this function. It turns out that it's very difficult to integrate a trigonometric function that's being squared, with a couple of exceptions. Sine squared is not something that is readily integrable. That's actually not the right term to use, but it's not something that's readily that you're readily able to take the integral of using the techniques you talk about early on in calculus. So what we use this for is to take that trigonometric function, that sine squared, and put it into a form that's easier to integrate. And again, I can't, without taking you through a calculus course, I can't really explain to you why this is easier to integrate than this is. So you kind of have to take my word for it until you get to calculus 2 and see for yourself why that's the case. So that's sort of a little motivation for what we're doing here. Let's go ahead and develop these reduction formulas. The key to getting all 3 of the reduction formulas that we want is to go back to those 3 different double angle formulas that we just developed for the cosine function. In fact, I say 3 because there's 3 of them, but there's only 2 that we need here. So to motivate the first one of our double angle formulas look like this. Cosine of 2x equals 1 minus 2 sine squared of x. I'm going to solve this equation for sine squared of x. I could subtract 1 from both sides and then divide both sides by -2. And what that's going to simplify down to, sine squared of x equals 1 minus cosine of 2x over 2. So again, that just came from solving this double angle identity for the sine squared. If I use a different double angle formula, cosine of 2x equals 2 cosine squared of x minus 1, that was one of the other ones we talked about, and this time solve for cosine squared. Same or similar steps, I would get cosine squared of x equals 1 plus cosine of 2x over 2. Notice how similar these look. The only difference is I have a minus in one case where I have a plus in the other. Finally, if I want a reduction formula for tangent, meaning I want to start with a tangent squared and reduce it down to an expression where all of my trig functions have smaller exponents, power of 1 basically. I don't need to go back to a double angle formula. What I can do is just use the identity that I already know for tangent. Tangent squared is equal to sine squared over cosine squared. Sine squared is the same thing as 1 minus cosine of 2x over 2. That's from what we just got up here. Cosine squared of x is equal to 1 minus cosine of 2x over 2. And that should be a plus. Little typo there. That's easy to fix. 1 plus cosine of 2x over 2. So I'm just using these and creating a quotient out of them because that's what we get to do with a tangent. The 2's in my denominators can cancel out, and I'm left with 1 minus cosine of 2x over 1 plus cosine of 2x. Those are the 3 reduction formulas. Now, ultimately, you do want to have these memorized. Because again, by the time you get to calculus, you're actually using these a lot. But while you're still working on memorizing all of these different identities, it is really, really helpful to remember how we derived them in the first place. Because I'll admit, like if I go a long time without using any of these identities, I sometimes forget which one has the minus, which one has the plus, and stuff like that. But if I know my double angle identities, I can just derive them because it doesn't take a whole lot of work to get these, you know. But I digress. All right, let's take a look at an example. I'd like to use the power reducing formulas or reduction formulas to prove this identity. Now this is kind of a wacky looking identity. 10 times cosine of the fourth of x equals this big thing. 15 over 4 plus 5 cosine of 2x plus 5 fourths cosine of 4x. How do we go about this? Well, what I'm going to do is take the left-hand side and start there, because it would make sense if we're using power reduction formulas to use the side that has a large power of cosine. Now, the 10 is going to kind of stay put there, but cosine to the fourth of x. Notice I can write that as cosine squared of x squared. After all, raising something to the fourth power is the same thing as squaring something and then squaring it again. We know that from our exponent properties in algebra. The cosine squared of x here, though, is the thing that I get to use a power reduction formula on. What does that look like? 10 cosine squared of x, remember, is equal to 1 plus cosine of 2x over 2. And I'm squaring that. Sorry, that's sloppy, but that's a cosine of 2x there. Okay? Next thing I would want to do is just do kind of the algebra here. Square this quotient, meaning I square the numerator and I square the denominator. The 10 is still just along for the ride. 10 times... Now you have to be careful because you're squaring a binomial here. It's not just 1 squared plus cosine squared of 2x. You have to actually FOIL that out. It becomes 1 plus 2 cosine of 2x plus cosine squared of 2x all over 4. Okay? Now notice here, there's a little bit of simplification that can happen. So the 10 and the 4, I can divide each of those by 2. That becomes a 5. That becomes a 2. And what I'm going to do next is separate this out into 3 separate fractions. So this is equal to 5 times 1/2 plus, let's see, this 2 and this 2 will cancel each other out, so that just becomes plus, what is it, cosine of 2x. Okay, and then this becomes plus cosine squared of 2x over 2, or I could also call that 1/2 cosine squared of 2x. Okay, so that looks fine. Now, I'll leave the 5 out here for now. I still have one of my cosine functions being raised to a power, so it would be good to use a power reduction formula on this term as a follow-up step, and then see what happens with that. 1/2 plus cosine of 2x. I don't really need to do anything with these guys. They're fine for the time being. But what do we have now? Plus 1/2 times, well, cosine squared of 2x. I know with cosine squared, the power reduction formula is what we did before, 1 plus cosine of something, 1 plus cosine. But this time it's not going to be 2x, because again, what's really happening with this power reduction formula? Compare the angle on the left-hand side to the angle on the right-hand side. If I start with theta, then on this side I'm going to have a 2 theta. In other words, we double whatever angle appeared here. Well, this time the angle that I'm starting with doesn't look like just an x or a theta. It's a 2x, and I have to double that, giving me 4x over 2. Okay? And at this point, it's just a lot of simplification. So notice, first of all, if I were to multiply this 1/2 in, I would get 1 plus cosine of 4x over 4. And then if I separate that into 2 fractions, which which I'll do this up here. This is equal to 5 times 1/2 plus cosine of 2x plus, so this would be 1/4, and then this would be cosine of 4x over 4, which I could also write as 1/4 cosine of 4x. Okay, now let me take a look at the two constants here, 1/2 plus 1/4. Those are like terms. I can combine those. 5 times 1/2 plus 1/4 is equal to 3/4 plus cosine of 2x plus 1/4 cosine of 4x. And finally, to wrap everything up, let's go ahead and distribute the 5 in. 5 times 3/4 is 15/4 plus 5 cosine of 2x plus 5/4 cosine of 4x. And that is exactly what we were being asked to prove, okay? So this process is really, really reminiscent of what you do in calculus 2, starting with cosine or sine of something to, a large power, and sometimes using multiple applications of a reduction formula to get that thing entirely down to cosines of possibly different angles, but not raised to any power other than 1. Okay, that's going to be it for this video. We'll keep going with half angle formulas in the next one.